Now we're going to take a look at our differential length, area, and volume for our cylindrical coordinates. And so for more information on this, you can see page 62 in the textbook. And so similar to what we did with our Cartesian coordinates, we're going to start with this figure here, which shows sort of a little differential volume in a cylinder. So from that, we can define our differential displacement, which just like with our Cartesian case is going to be a vector. So differential displacement. So again, this is a vector quantity. And so we're going to define that as dl is equal to, so now in our row direction, we're talking about this as we go from S to P, for example. What we have is d rho in our row direction, so simple enough. Now in our phi direction, so as we're going, for example, from P to A along this arc, we can use our trigonometry or geometry to figure out that that should be rho d phi in our phi direction. So it depends on how far out we are from the origin, so what our rho value is. And then finally, for our z direction, so we can consider going from B to A here, it's going to look the same as we saw with our Cartesian. It's just going to be dz in our z direction. So that is our differential displacement. And again, depending on how we're moving, we might have one of those terms, we might have two of those terms, we might have all three of those terms. So for example, if we're going from point P to point A, we're only going to have our term in our phi direction because that's the only thing that's changing. Our z and our rho values are not changing. Just like with our Cartesian case, we don't need to include negative signs here. Any negative signs due to going in the opposite direction of our unit vectors is going to be accounted for by our limits of integration. So now let's take a look at our differential normal surface area. So differential normal surface area. And so just like with our Cartesian case, for our cylindrical, this is also going to be a vector quantity. And so same basic definition here. So let me put another figure up so we can sort of see what each of those surfaces are. So for instance, we have sort of the front surface. So this APQB is our first figure here. We also have a component in our z direction. So for example, that would be DABC. So that would be this middle one. And then we have a surface for the top of this little differential volume. So this would be, for example, ADSP. So that would be this one here. So this is just going to help us visualize a little bit easier what these differential surface components are. So we have three possibilities, just like we did with Cartesian. So of course, there's a lot of parallels between these three coordinate systems. And so what we're doing is we're calculating the area of this gray point, because in general, again, we're going to have ds is equal to some differential surface area ds times a unit normal vector un. And just like with before, if we have a volume that's enclosed by the surface, then that unit normal vector is going to be outward. So for this first one shown in A here, we're going to have rho d phi dz in our rho direction. For our second one shown here, we're going to have simply d rho dz. So d rho dz in our phi direction. And then finally for this one here, we're going to have rho d phi in our z direction. So again, each time what I'm doing is I'm just multiplying this term by this term to get our area, and then we're putting it in the direction that's normal to that surface. So these are our three possibilities, and of course each of these three can also be negative. So each of these can also be negative. We just have to consider which side of the volume it's on. So for example, coming up to this figure, if we have the surface ADCB, that's sort of on the back side. So that's going to have a normal vector in the positive phi direction. So we would use this component here. However, if we're looking at the opposite side, PSRQ, so that's the side of the surface close to us, that's going to be in the negative phi direction. So we'd have the same area, but we'd have to have a negative sign with our unit vector here. Okay, so finally, we can talk about our differential volume, which again is going to be a scalar. So differential volume, and this is a scalar quantity. And so just like we did before, all this is going to be is the volume of this little differential piece shown in blue here. So we have in this case that dV is equal to rho d phi dz. And so what we can see is that's basically just taking each of these three components and multiplying them together. So just like with last time, what I would recommend doing is spending most of your effort sort of becoming familiar with this figure and with this equation for our differential displacement. And then if you know those two things, it should be relatively easy to figure out our ds as well as our dv.